We still need to find the equivalent synthesis filters if we apply the inverse transform for the perfect reconstruction of our signal. We get perfect reconstruction, the original signal, if the transform T is invertible. For mathematical formulation of the inverse transform, we can again write the reconstructed signal x hat as a sequence of blocks, like we did before. We can obtain the reconstructed signal by simply multiplying the blocks of subband samples y of m with the inverse transform matrix, so given here. The elements of this inverse DFT matrix are given by this equation here. Now equation 5 can also be written as this here using rows times columns. So we have the sum, k going from 0 to n minus 1, n is 0 to n minus 1. That's equation 6. To see the resulting impulse response of the equivalent synthesis filter bank, we need the equations for upsampling and filter in the synthesis filter bank. In the synthesis filter bank, the subband's signals yk of m are upsampled first, and we obtain the upsampled signal with phase 0 and time index n because we are at the higher sampling rate. The following filtering is the convolution with the synthesis subband impulse responses gk of n, hence we get the output of the kth filter as given by equation 7, where L is the length of the synthesis filter. We assume that L is a multiple of n, which we can always obtain by appending zeros if necessary. Observe that most of the samples of y upsampled n are 0. To rewrite this equation here such that we only process the non-zero samples, we again use the blockwise processing by substituting n by m times capital N plus n and n prime by m prime times capital N plus n prime, using block indices m and m prime, and in block or phase indices n and n prime to obtain this double sum here. Here we can see that we get the non-zero elements of y upsampled of n if its argument is integer multiples of n, and we get this if we have n equals to n prime. Because of this, the inner sum only consists of one summand, because the sum over n prime disappears. So when we make n equals to n prime, we will have here the inner sum consists of one summand, and the sum over n prime disappears. So we end up in this case here. For the reconstructed signal, we simply add up all the n subbands. So now we're adding up the n subbands. From here we add up all the n subbands, and here we can now replace the y upsampled k m times n by yk of m, since we now address only the non-zero elements. And we reach here equation 8. This is now our reconstructed signal, where the first sum is over the subbands and the second sum is over the blocks. At this point, we can compare this filter bank equation 8 with the synthesis transform of equation 6. And we have here equation 6. We're just repeating it here, and we can compare with equation 8. First, we see that the transform of equation 6 has no sum over the blocks, meaning the filters only have length L equals to n, hence the inner sum disappears with m prime equals to 0. With this, equation 8 becomes this equation here. And when we compare this with the transform equation 6, we can see now the equivalent impulse response are given by jk of n, given by this here. Looking at our transform matrix, we see that these impulse responses correspond to each row of the inverse transform matrix, non-reversed. In conclusion, the impulse responses of our subbands are the rows of the synthesis transform matrix, here not time reversed. We can read out the impulse responses of the synthesis filter bank from left to right in each column of the transform matrix. Observe, each time we got our result by comparing the convolution sum of our equivalent filter bank with the transform sum.